Okay, I got an email. Here's what it says. It says, "Hello, dear Gary. I have seen a nice post over high impedance and BJT transistors. I don't know if you have covered everything since there are two schematics, etc. Please help with that. On the other hand, it says, I'm looking to make a simple but effective guitar EQ that can work with any amp, headphone amp, big amp, etc. So I assume he's talking about probably guitar amp or maybe a headphone amp that's made for guitars. Big amp, maybe that's a power amp. Not sure, but would it be possible, etc., as effective and universal as possible? Okay, so as effective and universal as possible. I think that means that it has to have kind of a high impedance, 1 meg, I would say, so that you could plug pedals into it or guitar or whatever. Bass treble, bass and treble, or with bass mid and treble, just transistors. So, yeah, I can do that. There are a lot of different ways to do that. And I'm just gonna, I solved it in one way. There's more than one way to solve this. I'm not gonna when I do this, I'm gonna just use a couple transistors, no inductors, although I love using them. I'm not going to do it for this. Here we go. So first thing to look at is this is basically the Marshall tone stack. Now these tone stacks actually, in my opinion, they do not make good guitar EQs, because when you plug your guitar in, when you're going into a guitar amplifier, it already has this mid scoop built in, and let me show you this. Okay. This is the trebles all the way turned up, the bass is all the way up, the mid is down, and what you get is this scoop here. Now, even if you turn it up, I'm going to use this Duncan's tone stack calculator. Even if you turn up the mid, this is with everything in a maximum. You can see there's a big dip here. I mean, 10 decibels here. So this is when you turn your mid up, there's still a giant scoop there. Giant in terms of equalization for sure. Now, if you're this is sort of a standard Marshall setup. If you go to like a just you make it arbitrarily large, you can see the loading effects. See if this will go up there. Nah, we'll go with okay, I put like 100 megs there. You can see that brings up your bass there, and that can still give you a little bit of a mid here, but you're stuck there with this dip here, and there's really no good way to get rid of it. It doesn't make a bad, if you want to pedal with the tone stack there, it's fine, but there's not a great way to get rid of this. They do a lot in this circuit for the minimal amount of parts that are there, but it's just not easy to get around that. So saying that, let's take a look at this. I'm gonna sort of nab this tone stack and sort of change it a little bit. I'm only going to use the kind of the signature dip in here, and I'm going to forget about the bass and treble and address those in a different way. So what I've done here is I've just changed this pot to just a steady resistor there, and then I've just redrawn it this way. The bass, this is the bass control. I've set it just infinitely high, and when it's that high, basically you can just remove it from the circuit, and then you're left with this here. And I can prove that to you if you want to see that it looks the same. I mean, here's the original, here's the new one. Now this has the it has a giant load on it, so it looks a little bit different. Let me just kind of show you what this looks like here. Okay, so we'll add a load to it. It should look pretty similar. So yeah, very, very similar. So I guess I've sort of converted this to just a mid, just a mid cut. And then I'm going to do something different. Basically, you can redraw it this way. In this leg, you can kind of just omit this because it's the impedance across here is low compared to 220K. So this is just as sort of this wire there, and then you just kind of redraw it this way. It's not entirely correct, but it's a pretty good estimate, and you can see here. Let's compare these. I'm going to add a load to this just so we're comparing apples to apples, so to speak. So here's what I said, redrawn. Here's another one. You can see it's real similar. I'm just eliminating unnecessary parts for our thing. So here's basically the mid cut I'm using. And what I did is I also just kind of rewrote this 22 nanofarads to 22,000 picofarads, so you could see sort of the ratio of these things. This is like I think it's 47 to 1, or let's see, 22,000 divided by 470. Yeah, 47 to 1. And this here, 220 over 33, is a is like a ratio of 33. So we've got 220 divided by 33. Well, I'm sorry, that's more like 7, ratio of 7. So these ratios become important when you're trying to shape the mid control, and I'm not going to get into a lot of that, but so now this is something I'm not going to go into great detail here, but rather than writing it this way, I'm going to actually sort of invert this. You can invert a lot of these filters, passive filters, a lot of times by changing the resistors to capacitors and sort of inverting the ratios and so forth. So what I did here was I first chose 100K because this is what I'm going to use in the upcoming circuit. And then if you look here, as I said, there's 100K divided by 47, because we said there's a ratio of 47, is about 2.2. Closest resistor I have. So we've got this ratio here, and then the way you figure this out, and I'm not going to kind of whiz through this here, but okay, so what we've got here is, let's see here, yeah. Okay, this is the formula for the frequency of the notch. It's frequency 1 over 2 pi square root of RC, of the 4, you got 2 capacitors here, 2 resistors. You just multiply all those together. And so this is sort of a constant here because we're trying to keep the frequency the same. So we've got these two. To get these two, we know that there's a ratio of 7 to 1, and we also know that the product of these 4 equal the product of these 4. So basic algebra gets you down to something similar to this. So let me close this. And I'm not going to go through that because it's algebra, and anyways, you can also just play and toy around with it, but this actually was not exactly. It came out to be, I think, 0.16 or something like that, but I just kind of chose this because I'm just kind of roughing this circuit in, and let's see what these things look like. Just let's go ahead and run this. Got, let's see, where were we? Okay, this was the Marshall tone stack. We eliminated one of the capacitors. Looked very similar. This is the inversion. Let's see what that came out like. Now that's a little different. I have a different load on it, so this load effect you see here is not there, and I can show you that. Like, if we're going to compare these things, you can see these load are 512K. I'm just going to make this arbitrarily large, and you'll see that they should look pretty similar. See, there's this one, there's that one. They're darn near close. So we've kind of successfully inverted this. This notch is very similar. The only thing left to do for applications, if you wanted to use this in something, would be scaling it. You know, that's like you can multiply all the resistors by 2, then you divide all the capacitors by 2. That's just call that like filter scaling. You know, it just depends. When you're trying to match impedances, you need to do that a lot, and we'll of course kind of see that down here. So now this, what I did here is I've just built a few of these notches before, and I kind of generally aware how they behave. Now, if you make the legs of, well, let me back up for a second. This Marshall notch here, one of the things about it is at low frequencies and high frequencies it has different impedances, so it makes the notch a little bit sharper, but it makes it a little harder to deal with when you're inserting it into a circuit, because you got to have a kind of a lower impedance leading into the circuit and a higher one later. If you want to sacrifice a little bit of the width of the notch, or what they call a Q, a little bit wider Q, you can get like a little bit steadier impedance across all the frequencies. And so you can do that by making both of these legs equal. You can also make them equal up here if you wanted. The way you do that is you'd, you know, just for curiosity, 220 times 33, you multiply the two together, and then you take the square root. That's like a geometric mean, they call that, and that's how you do that, because you want to keep the frequency the same. You can't just, you know, average them. It has to actually be, you multiply them together and take the square root. So if you change this to 85, this to 85, the frequency would stay the same, the notch depth would change, and you'd have to adjust that. That's kind of what we're doing here. It's exactly what we're doing, really. And what I did is, instead of having this 47:1 ratio, it ends up being a 1:10 ratio. And you'll see that it's not as steep as a notch, but it's not bad. I've used it before, and let me just kind of run this and show you what that looks like. We've got equal loads on both sides. It's arbitrarily high, 100 meg. So we've got this notch here. That's what it looks like. Now this is kind of a steepish notch, kind of like the Marshall notch. This is not going to be as steep. Okay, you can see it's a little bit wider, and the frequency went down. Now I can adjust these things. If you adjust this ratio here, the depth will go up or down. If the more different these are, the bigger the depth, but the wider the Q. And if you, sometimes people do like a 2 or 3:1 ratio here, and like, you know, 20 here or whatever. I just did like I just did this equal arms and 10-to-1 ratio, which is kind of pretty usable. So anyways, I'm moving on. That's how I chose to make this dip. It's kind of starting with the Marshall, deviating a little bit for the sake of making the circuit easier. Now, this just shows this next circuit and the difference between these two. If you insert a resistor here, like a larger one, or if you even take this one and just kind of crank it up, it prevents the signal from going through here, or in another way, you could say the notch depth, because this ratio is changed, gets less. And let's look at the effects of inserting a large resistor there. You can see there's the notch. The notch is gone. The blue line up there is, there's a little bit of a effect here. It's basically, gone. And this is how I'm going to make my mid control. You would use like probably a 1 meg. I kind of look at how big these are and go about 10 times higher than that and make it logarithmic, and that will make a pretty decent control. Later on in my experiment, I did something a little different. I'll explain it later, but that'd be like the best way to do it. Would be a 1 meg log or audio taper pop. Now moving on, here's the mid control. If you bypass this leg here and just kind of like put a huge capacitor across it so there's an AC bypass, or even really just a wire, what you're going to get is a base, well, it would be like a high pass filter. So I'm going to turn this mid control down to 1, turn this base control down to 1, and you'll see what it looks like. It's basically you can see this big long, it's a high pass filter. It's reducing the bass. And tell you what, to give you a better idea here, let's move this, turn the mid down on this one so you can see the original scoop there. There's the mid scoop. There's this is it, converting it to the bass. So you can't, one of the reasons I put this capacitor here is because later on the circuit's needed, and I'll show that to you. I don't want to really, well, I'll just illustrate it in a few more circuits. You can put a wire across there if this is all you're doing, but I'm kind of running it into other circuitry, and that in AC bypass is better, just using this capacitor there. So I'll sort of point that out coming up here. So here's the mids. So we've got a mid control right here. Here's the base control going right across here. I showed you how that worked. And this whole thing, we're going to step it up to about 5 times the impedance. So the output impedance, we're going to kind of step it up a notch to 500K. Now usually you go from like 100K to 1 meg. That would be 10 times. Anytime you're going from one stage to another, you want to increase the impedance by a factor of 10 to avoid signal loss. However, I'm really squeezing this in to just a couple transistor circuits, so I'm kind of cheating a little bit, and I'm just going with 500 for now. So anyways, this becomes, this is just a high pass filter. You got a resistor and a capacitor, and this, you can turn this up or down, and that basically will adjust the treble there. So let's see here. So let's see if I got anything right. Yeah, so there you can see this is the mid's going up and down there, and this is a treble. This is a treble cut. You can see that there. And anyhow, So now this I've just kind of brought back the next couple circuits are kind of the final circuits, and I'll explain them. Here's the original Marshall tone stack, and I've got a really high load on it because I want to just compare. I don't want to see those loading effects on the bass. Now here's the circuit. We've got the mid control, the bass, and the treble. Now I didn't really want the if the bass goes to 0 and this goes to 0, it's like it's just too much of it. Cuts into the mid-range level and everything. Basically, what I did here is I did everything by hand. I took a 1 meg pot and I sort of had guitar playing through it, and I adjusted this bass up to the maximum level and a minimum level, and I recorded them. And the minimum level I wanted was 33K. It was too much of a cut after that, so I inserted this 33K there, so this never goes less than 33K. Else it just kind of wipes out the mid control. It goes down too low. I did the same thing with the mid and the treble, and just kind of adjusted things, Now, to explain a little bit more, one reason I had to put this capacitor in here, as I mentioned before, is if you turn this down, then it sort of it's going to end up affecting the bias of this transistor. And let me explain this a little bit. This here, I use this all the time. Usually I have a 3.3 meg right there. It's really simple. You've got just 4 parts there, and it turns this transistor into a high impedance buffer. Works very well. It's not extremely precise because it depends on the gain of the transistor, and that varies by batch, but as long as your gain is around 300 or I tested like hundreds of different 2N3904 transistors. They're all above 100 for me. I'm sorry, all above 300. So that's never a problem. But basically, I'm going to change this to we're instead of looking at the Bode plot, that's what we were looking at before. We're going to actually look at the signal for a second. Here's an initial signal. You can see a little closer there. It's just a 1 volt signal. Let's see, zoom to fit. Okay, and what I'm doing is I'm showing the bias here. The bias is like kind of the DC that it's riding along. So this puts it at about 5.6 volts. You can see when you step down here, this they call this an emitter follower. Basically, it copies the signal and puts it down here 0.7 lower, and you can see that happening when you go from the blue to the red. It steps down by 0.7. Now I did something, one of the reasons I never mentioned this really, but one of the reasons I inverted this bridge T filter, which was what we were working on, and have a resistor here rather than the capacitor is, I didn't feel like rebiasing the output. So this is an input buffer, this is an output buffer, and I get to skip these 2 parts because I'm just going to use, this is at 4.9 volts. I'm going to step that down again. It's going to be 0.7 less. Now there's a little bit of variability because when you insert this resistor and this one's going up and down, it's going to actually move this bias up a little bit, but it's not too much. You can see it goes from 4.13 to 3.8. So that doesn't really matter that much. You lose like a little headroom using the circuit this way. But for a guitar, it's unless you have really super hot pickups and you hit it as hard as you can, I don't think it's going to clip. Even if this HFEs are off a little bit from 300, it probably won't. Anyhow, So it's another reason I had to put this capacitor in here. I might have mentioned that, but you know, you can imagine it would totally drag this voltage down if this capacitor wasn't there. So this is pretty much it. I built this circuit here. What I did was, I mentioned the 1 meg mid and base controls. This would be a linear control. These would be audio. However, I don't keep around a lot of audio taper parts, and what I usually do is just try and substitute the best thing I can with a linear part. And what I did was, the mid control, instead of using a 1 meg audio taper, I used a 250 linear taper. Now, how did I figure that out? Well, I didn't. I actually just sort of I put in the lowest pot that I could, where you really couldn't tell much of a difference. Now, going between 250 and 1 meg, you could hear just the slightest difference, but it really didn't matter that much for the purposes of a circuit like this. And I also did the same with the bass. By only going up to 250, there's a little bit of a bass loss that you can hear, but it's very subtle, and I don't think it matters that much. So anyways, I just did everything by ear, and then basically, instead of using a 500K, I just sort of simulated it with a 250K, and it seemed to just work better. And I would just insert different values of capacitors until I got something I liked, and that's what I came up with. And I don't want to use really expensive parts for this. I mean, this is just a simple project, stuff you could do with things you probably have on hand. So I'm just and I think probably the bass would be maybe a little better 500K, but there's I don't know. This is okay. So let's see what that looks like. I'm gonna change this, kind of show you what, I did it by ear, and it was acceptable, but when done by ear. But let's see what it looks like. I'm just setting up this Bode plot. Okay, so what I'm doing here, this is the Marshall. This is what I ended up doing by ear mostly. Let's see what we've got here. This is sort of the Marshall. Well, this is it right here. Let's look at this one. Okay, it's different, of course. It's a different circuit. You can see that, I know this is a little bit messy. Let me remove the phases. Okay, the green this is turning up and down. The bass control is up and down on the mids, up and down on the treble. So this is sort of what the Marshall looks like. You can see you can't get, you're really missing a lot of mid there. No matter how you turn everything up, you've got this dip there, and you just can't get any higher. Let's see, compared to this one, you can see you're down at about -2 decibels in the mid range, -1.65, and -3 there in the sort of the bass range. Now you might say that's a lot, and compared to a Marshall tonestack it isn't, but anyhow, by ear, the guitar sort of has this big spike in the mid range. It's a real big spike, and so you got to look at this thinking like, well, what signal is going in? And like I said, I've done this by ear. It sounds okay for what it is, and it's very, very simple circuit. And You can do I can do things differently, but I think this is a pretty good compromise for making a simple circuit that works well. Number one, let's kind of review what's going on here overall. Because the fellow wanted something that's kind of universal. Now, it's got an input impedance of about 1 meg, and I'm going to show you how to do that real quick, just for people that are interested. What you do is you take the, I already know that just by looking at it, but just to test it, you've got, you take the voltage divided by the current, you divide the two, and I'm just going to get rid of this because I don't like looking at it. I'm going to get rid of these phases too, not interested. I'm going to change it to manual limits. Instead of decibels, we're going to look at linear. And this should give us, and then I'm going to zoom to fit. Okay, so you can see there's a variety of different impedances here that this voltage source is seeing. That's because when you change all the controls, the impedance changes somewhat. So we've got a range of about 852K up to about 1.2 megs, and most of the guitar signal is in this area anyway, so you're looking at like there's 1.1 meg to 1.24 meg. So this is above 1 meg input impedance at 1K. So that's pretty good. It's not as easy to illustrate the output impedance, but basically it's the impedance of all this stuff, which is, you know, in the, in the, I don't know, 500K range. And then 500,000, and you divide by, well, yeah, you divide by the HFE of the transistor, which we say is about 330. So we're looking at like 1K. That's kind of, it's a little higher than I thought it was going to be. Anyway, 1.5K. And that's not bad, because basically the fellow wanted to run it into just about any amp. And, you know, power amps, you know, usually like 22K, 33K input impedance, sometimes 10K. If you got like a headphone amp for a computer speaker, it might be 10K input impedance. Now mixing boards, like low impedance mixing boards for microphones and stuff, are going to be lower, but you know, this, I don't think you'd be using this as a microphone. No, you didn't really mention that. You said more like guitar, so I think it's going to be, you basically need like 10K or above that you're going to run this into. So you can run, you've got a high input impedance, and for most guitar type purposes it's going to be acceptable. Even what you call consumer amplifiers are usually 10K or above, and that would be like just computer speakers or something like that, or maybe your auxiliary input on an auto or something like that. So this is kind of as universal as possible. Now you can add 2 more parts and get this super low by just linking another one of these there. You can drop it by another 330, and I guess I could show you that since I'm mentioning it, but you'd kind of, you know, drop the, well, anyways, I'm not going to get into that right now. This video is going on too long. You can link another one of these up and lower it to, like, you know, sort of the range you'd see with an op amp. So now I did add a few parts here, and what I did here is you can actually, if you want a volume control on this, where you have this 10K, you can actually put a 10K pot here and put this on the wiper, and when you move it up and down, it becomes a volume control for it. So it's like an extra control if you want to do that. And there's also something else I normally do when I use these, is I'll put like a series resistor here of about 1K. and I also usually put one here. You usually see them on pedals. I do this because when you use an emitter follower to go into something else, occasionally I've had high gain circuits in other areas, circuits that I've gone in, fed things into where you can get oscillations like parasitic oscillations, and normally that's cured by just a little blocking resistor. So I just put it on there. I don't know. I don't even know if it's needed. I didn't do it and it worked fine. I never need this either. Well, I'd say never, but I didn't use it in this circuit and it didn't matter. But I think sometimes it avoids problems in the circuit just by putting a little series resistor. I've noticed that. Sometimes they even put one here right before this input, but anyways, this one, if I say I had to make a PCB board, if I ever do that with this, I would add these extra parts in. But this one here has about 18 parts as I count them. Get out a few more to ensure stability. And I think this extra control is nice. One thing to note though is when I say 10K pot here, you get those 10K pots, they're often not 10K. Sometimes they're like 8 or whatever. Who knows what you're going to get. So you got to keep that in mind. And one thing you can always do is, if you're not sure about the gain of your transistors, you don't have very good equipment, if you just have a voltmeter, you can check these voltages. See, this voltage is 4.8. If you get something with a low, really low HFE, it will drop down. Same here, like if you get a 10K pot and it's not really 10K, this thing here may drop down below 3.8 to maybe 3.5 or something like that. Anyhow, that may not be a problem. It might if it's a really bad pot. Anyhow, so this, I think that's a very long-winded discussion about solving this problem, but now there were other things I did. I'm just not going to get into them too much. But I had a Darlington configuration with some inductors, and that was a 2 transistor thing. That's kind of neat. I've also got a really cool inductor-based EQ that I might show sometime, just because it's conceptually it's pretty cool. It's really minimalistic also, but it requires you really going to like a really low impedance. But anyhow, this seems to work, and I hope that answers your question. There are other ways to do this. I don't know of an easier way to get high input impedance and low output impedance with 2 transistors and 3 or 4 controls. This is probably one of my best takes on that. Now, if you want to do 3 transistors, that really frees things up a lot, because you've just got you can just buffer between filter stages. We've got 3 different filters between 2 buffers. That's kind of hard to do. I mean, this is about as much as I think I can do. So hopefully this answers your question, and if you decide to try it out, let me know. I might post a second video showing like white noise and the spectrograph on it, or whatever you call that. But thanks for watching.